And once you know it, I was talking with a gentleman from Washington City at lunchtime. And how many of anybody from St. George area here today? I'm sure there's people online. Everything down there, just about, I think I mentioned this earlier, is in the attic. And it really is kind of it's just a poor place for it. So let's talk a little bit about what the 18 code started and the 21 code really moved forward. And it is basically, it defined burying the ducts explicitly in the code. And as we talked about just before we broke, there is some concern about burying ducts in insulation or having ducts inside the thermal envelope or near the thermal envelope where it can condense when we're in humid climates. We don't have that problem. There is absolutely no reason not to bury our ducts in the insulation. So whether we do any of this extra stuff I'm talking about, our ducts should be buried in the insulation. Now I have people saying, well, wait a minute, I've got R38 in my attic, and if I have the duct down in the insulation, I don't have a full R38. Well, yeah, kind of. So what do we have underneath it? We have 3.5 inches if it's laying on the trusses. And so we're going to have someplace around 13 to 15 underneath it. And then to get our 38 or 49, we're going to be close to coming up to the top of the duct. But irregardless, if we're just exposing a little bit of the duct to the hot climate in the attic, we've drastically reduced the amount of heat flow or the heat conduction that occurs from inside the duct to the attic or attic into the duct. So please, anybody listening, do not ask your contractors, your HVAC contractors, to suspend them above the insulation. Put it down in the insulation. The 18 code has a means to characterize the performance of buried ducts as an equivalent duct insulation. And basically what it's saying is it's identified if you're partially buried, it's equal to, and I can't remember the number, a certain R level. But if it's completely buried, like we talked about, every time I go for a while with this, I have to manually move my slide. If we're partially buried on either one of these diagrams, so the duct's poking out the top, we're still really reducing the area it's exposed. And this area that's down in the insulation is seeing an effect of greater R value. The 18 code gives us a simplified credit for buried ducts in the performance path, which is that modeling. And we can even call a duct inside the space if certain requirements are met, and that is when we do this, when we encapsulate it, or if we bury it with at least 3.5 inches over the top, we basically consider it inside the space if it's sealed well enough.
So are you still going to require it to be wrapped in R8 insulation if you fully encapsulate it?
Well, it has to have the R8 and then you have minimum 3.5 on top. And in colder climates, I mean in humid climates, then it's even more than R8. But yeah, you still have the minimum R8. Just kind of to drive this point home, I did a simple calculation on 25 feet of 6-inch flex duct. Now you buy flex duct in 25-foot lengths. And I just wanted to show what the exposed surface area is on that flex duct, because that's what we're looking at when we look at a thermal analysis of whether we're flowing heat through a wall or from a duct. We're looking at it, the exposed surface, you know. And so I took the 6-inch flex duct, 25 feet in length, diameter times pi equals the circumference. 0.5 times 3.14 is 1.57 feet. So that's the circumference. So the area that's exposed, multiplied by the 25 feet in length, you have 39 square feet of exposed duct. Now it has R8 around it. You know, I'm doing the calculation on the actual liner inside the duct. And this is our heat flow equation, and it's a real simple equation. We talked at a break with someone about conduction. If you take the U, which is 1 over R, multiply it by the temperature difference, times the area, we get the amount of heat flowing. If you just take U times the temperature difference, and I really wish I had a whiteboard. If I have a 0.5 window, so for my example here, if I have 0.5 U factor window, and I have 100 degrees of temperature difference between inside and outside, and I know that's a crazy number, but it'll work in the equation. So 0.5 times 100 is 50. I will lose or transfer 50 BTUs for every square foot of that window. So it's just U times the temperature difference. So U is directly related to the insulation, right? So the better the insulation, the smaller the U, the less amount of heat that's going to flow. Or if you change the delta T or the temperature difference, you know, it'll either increase or decrease it. So it's just those two factors. So you just take those two factors times that area, and you get how many BTUs of heat's going to flow. So for this one piece of flex, with R8 flex, so they use 0.125, and an attic temperature 145, 55 degrees inside the duct, because that's the temperature of the cooling air. You have a 90-degree temperature difference, so 1.25 times the 90 degrees times the 39 square feet of exposed surface. And we have 439 BTUs for every 25-foot length of flex. If we could bury that flex in the insulation, we drastically reduce that number. If we suspend it up in the attic, then that's what's going to happen for every 25 feet. Now you go into an attic full of an HVAC system, and you're going to see all of these flex sizes in a residential home. That piece of 20-inch flex that they run over for a return, 25 feet of it's almost 1,500 BTUs just for that one piece. So we can see with all these different lengths of flex that are strung all over in an attic, we can have 1 ton, 2 tons, even 2.5 tons of cooling required to overcome the heat gain through the duct. We just got to bury it in the insulation. Any questions? I know that's a whole bunch, but I'm just trying to make the point of how much heat we gain in an attic when we put it in that hot attic, or how much heat we lose when we put it in a cold attic.
You know, how do you address it? I guess you would have to do it ahead of time, because as an inspector, by the time you notice it, it's done. And you're not going to come back and change it because they don't have to. So what do you do? Is it a plan review say, hey, this is where it's got to be? Is there any, you see, other than just playing to their, hey, this is the right thing to do?
Well, that's a great question. The 18 code actually starts giving us some ability to identify in the code that, yes, we're supposed to bury it in the insulation. What we shouldn't do as code officials is we should never tell them, I want you suspending it above the insulation.
Right.
Because there's nothing in the code that says we should do that. And the 18 code does acknowledge that we're better off buried in the insulation. 21 code even takes it a step further. And I think by the 2024 code, it's going to, some of these things that are kind of options in the 21 code are going to become mandatory.
I see them, half of them are strung up, and then they're kinked, and then there's, you know, I mean, I can't even believe they'd be efficient at all.
What you can do, what everybody can do, Have any of you ever been to the code hearings or the code development hearings? Kathy's been there. You've probably seen them get up every time trying to outlaw flex duct. And my good friend that's sitting up at the top of the stairs is Jody Hilton. You know Jody. When I've known Jody for years and years and years. We worked together on the original RMGA certification, 30 years ago and stuff. But when I first started inspecting, he says, Brent, we got to do something about flex duct. And he's right, we got to do something about flex duct. And so at the code hearings, all the time we're hearing, and in fact, the U codes, the uniform code even outlawed it, but then they put it back in for residential. But every time someone gets up to say that we should limit the flex duct or completely ban it, their comment is it's never installed correctly. And I think that's a safe comment, or rarely is it installed correctly. Why isn't it ever installed correctly?
Yes, yeah, they're always kinking it and they're always bending around the trusses and getting into.
Yep,
Weird
they're
places.
doing all that stuff. And guess what? They do it because we let them. We let them.
We have had as when we go with punch list mechanicals, that they go even commercial, and they say that is not going to produce the CFMs that I think that's why I did a 6-inch and not a 14-inch. And now you bend it, and now I don't even have to shoot it.
Yeah, you don't have anything.
Can you change it? And they said, no, there's no way we can change it. What you are saying, it's already installed, there's already stats everywhere.
Well,
there's everything done, and then
I
it's happening, but it fights.
code officials, building inspectors. It's crazy. You walk into that job to inspect it, and there's little half sheet pieces of paper, or there's bags that flex duct came in, and they all have installation instructions on them. And it says no kinking, no squashing. The radius of the turn of the duct needs to be the radius of the duct. So if it's a 12-inch duct, you need at least a 6-inch radius on the inside of the bend or bigger. It has to be fully expanded. These are all things in the installation instructions. And so the only way we're ever going to get it right, and this was we talked about earlier, sometimes enforcement has to be a piece of the solution. So I think I have a little bit in here on it.
Can that installation be collapsed at all?
Nope.
That's what it-
Manufacturer says 0.
Okay, perfect.
Manufacturer says 0.
So really part of the R value, you start compressing insulation.
You lose R value when compress insulation. You lose cross-sectional area when you compress a round pipe. The 18 code says you can't deform a dryer vent because when you start squashing a 4-inch, you don't get the airflow. So yeah, you can't squash it.
You showed that you wanted about 3 inches or 4 inches of insulation underneath the duct on those insulated.
Well, that's what you'll
ducts.
get simply because it's laying on the trusses.
Yeah, I mean, you're not gonna get your blow-in guy to go in and blow that, so that would have to be probably a bad insulation, wouldn't it?
Well, I think with a little direction, they generally can get it. And it does kind of settle
Chair
down
it up
into
or
there.
something.
It does kind of settle down into there. I'm more worried about above it than below it because what's below it, the interior space.
Yeah,
But even if it's just, some baby steps, that it has to be as straight as possible. No kinks, take the kinks out. That it's horrible that they stick this plenum this high up in the attic and then they have this explosion in a spaghetti factory appearance of flex duct running everywhere, and it's laying on top of each other and squashing it and everything else. They don't work. They simply don't work. The friction loss in flex duct is already about 12–15% more than it is in smooth metal duct. They have to oversize it anyway. I mean, it needs to be done right. And I think I have some more stuff a little bit later that we'll talk on that. But simply, and you can send me an email, and I have the Air Duct Council's installation instructions, which all the manufacturers state is their specification for their duct. And it goes through everything they're supposed to be. Supported every 4 feet with no more than 1 inch of sag in 4 feet. Well, I don't think you can support it every 4 feet and keep the sag that low. You're probably gonna have to support every 2 feet to keep the sag from being that much. I think it's a viable product if it's installed right. It's quiet and it's pre-insulated. So I see the value in trying to keep housing affordable, but it needs to be done better than it is. So garages, were you the one that were bringing up bonus rooms?
Oh, yeah.
Bonus rooms over garages are a big challenge because everybody's always complaining they're cold. And there's 3 or 4 factors to it. One of them is there's never a return there. So they don't have a return path to get the air back from it. But the big one is it's completely surrounded with unconditioned space. So almost the full bonus room over a garage is surrounded, is a thermal envelope, except for where you hook to the house through stairs or whatever. So we have all this ductwork in the garage ceiling that serves that bonus room over the garage. Or the rest is, my house is a 2-story, the upper floor just goes over part of the garage. How do we insulate that duct? And we've seen this, haven't we? Bunch of times. We have all this ductwork. The runs are going to upstairs. And how do we insulate it? Do you make them insulate the duct and then insulate underneath it? Or are they okay if they insulate around so that the duct is in effect up inside the conditioned space?
But you were to build a joist cavity with insulation and have an air barrier, and then maybe do continuous around the box out there, then it's all part of the conditioned space.
Yeah. That's kind of my interpretation, my recommendation. The problem with coming in and just putting batt insulation, so you put a piece of batt insulation in the upper right here, and you fit a piece of batt into each one of those spaces. We're considering 2 foot on center, so we can put a piece of batt there. But then it's not insulated above any one of those framing members. And what about insulation along this face or the face of the fur down? Are we getting insulation in there? So we try to shove some batts in there and we leave all this airspace up in there. And if we aren't insulated really good on the exterior or anywhere else, we're ended up with cold air migrating in through all these air spaces. And one of the production builders that I've worked with fairly closely has fought this problem because it's complaints. People are not satisfied with just kind of a warm space. 50 years ago, we were pretty lax about, if our house was within 5 degrees or something from one end to the other, we really didn't worry about it. Lots of people, we didn't even put air conditioners in everything. Yeah. I remember doing houses when I first started in HVAC. We did houses in Pepperwood, which was the elite neighborhood. And they would say, well, we'll wait till summer to see if we want air conditioning. Do we do that today?
No.
Every production home, every home built today ends up with air conditioning, right? And everybody wants it precise. So these are a problem and people complain more and more about them. So
Shouldn't so should the floor of a bonus room above a garage be treated as prescriptive code?
R30.
Yeah, right, exactly. The floor, and then that box out of that wall will be treated like any other above grade wall with the requirements of insulation, air barrier.
Yeah. But just what do you do with the duct?
Right.
How do you?
Yeah, encapsulate as part of it.
Can you go back to that last slide? And then the one on the picture on the lower right, I don't know if that's a return. Yeah, that one right there. That's just a pan.
It is.
So it's a return error. So yeah, you see that a lot, right? So you know there's nothing there. Cold air.
What it's hard to see, but what they've done is they've set it up so that you can get it like 1.5 inches underneath it.
Oh, underneath it, so I just-
They've set enough that they can get R8 under it.
Sometimes you see them where they nail it flat to the bottom
Yep.
of that TJI.
That needs to be, it needs to be either included in the drop, or it needs to be insulated with some rigid ductboard or something like that. Yeah, it needs to be insulated. It's outside the thermal envelope. So yeah, that's a great point. And the same thing for the pipes. You know, I'm pretty flexible with the guys on the pipe, on the galvanized pipe. But I told them when I was there doing the inspection, I said, hey guys, put your starter in and go up as high as you can in the joist space so you can get the maximum amount of insulation underneath it. I mean, this isn't rocket science. I mean, this is pretty simple stuff, isn't it? We just want to get it insulated. And I think we have, as inspectors, we have the authority to say, hey, I'm going to let you, I'm not going to make you wrap this all with R8, and then we do our thermal insulating for the envelope, but you need to do this. Don't shove it tight. Now, this is against the conditioned space, so maybe it's not so bad, but don't shove it, and the framer, don't shove it tight so you can't get insulation between the cold garage and the duct. Make sure we can get the insulation around it. It's like ductwork in basements, you know, the guys run it right tight against a concrete wall. How do you get the insulation up behind it? We, code officials, architects, everybody, we're constantly training the people that are installing them, whether it's by the directions we put on the plans or by how we do our inspections. So anyway, I really fretted with this when I installed a lot of these systems. And it's a pain in the butt to try to insulate them. And so blown insulation is about R4 per inch if they blow high density. So minimum 2 inches of space all the way around it. And here's what I think is a great system, because what does it do? It fills all those voids.
What about the OSB? Basically, what I'm seeing the OSB, the perpendicular one.
This,
Nope, up the next one, it's up, yeah. So
So
did
Well,
you
it's
feel
filled
that
inside there.
see those kind of like puncture holes through it? They stick
Oh, they you put a blow.
yeah, they fill it up.
blow it up.
They blow from below and they,
So you blew it up.
no, and this is a pretty good looking, they've done a good job of insulating that. And guess what the builder found out? That it works. But,
Probably less money.
I mean, it looks like it should work, doesn't it?
Yeah.
And the theory behind it is that we're going to get insulation all the way around it. We're going to make sure we don't have any voids and spaces in there where we can possibly have cold air migrating from outside. We completely filled it up. And it's a really nice job. And it costs maybe a little bit more than the bat installation, but boy, it's so much better job. I've become really a big fan of this type of insulation over the past few years, just because I've gone around with the thermal camera and seen what it does. Great product, really good product. If I were to build a house again with I'd do 2x6 wall, and I put foam on the outside, and I put an inch of foam on the inside for air sealing and stuff, and then I'd net and blow the balance of it. And I think that's probably a pretty good wall, and it's most cost effective. Trying to spray foam an entire stud cavity full of foam is way more expensive, and there's other ways to do it better. So anyway, I think that's a good solution. It's fiberglass, but it's
Blue.
Do you see cellulose at all for that?
I have rarely seen cellulose. I don't see cellulose much anymore except blown in attics. and I'm really not crazy about cellulose. I had so many people complain about dust in their house from cellulose insulation because it came in through the lights and everything else. And I put in air cleaners and stuff, but you can't stop it because it just keeps coming in. Do you have a comment?
No.
Okay. And I also cellulose, they treat it with boric acid, and this is kind of a little off. This is mechanical code. All these re-insulate attic programs that have been going on, we're seeing all this cellulose being blown in these attics, and they're blowing up against all fuel chimneys. And then the people are running their wood burning stove all winter long. And when I was at the county, I went on at least 7 or 8 fires that started in the cellulose around those all fuel chimneys. So I'm not a fan of the ground up newspaper. I know it's green and everything, but the chemical treatments just don't hold up. You know, they break down when they're exposed to heat over a long time. And it's just a smoldering fire. You know, it's not, it doesn't support combustion, but it just smolders, and then it, we end up with the damaged roof system. Equipment sizing. Those of you that know me know that I'm passionate about doing load calculations, right?
You taught me how to size gas line diagram.
I've taught you gas lines. We've talked about manual J's forever. And I was very fortunate back there almost 50 years ago that my boss taught me to do manual J load calculations by hand, which was the big paper that you spread all the way out and you looked up the heat transfer multiplier for everything. You wrote it in there and you put in your temperature difference and you did the math and you did a load calculation. And I did them by hand for years and years and years. And shortly after I started my own business, what came about, these first PCs, I paid $2,600 for my first computer. And it had a 20 megabyte hard drive, and that was the top of the world. And it was a color monitor, which meant it was more than just green. It also had yellow and other colors in there. But I had the first version of WriteSoft. I did my load calculations on that. They work, because what's a load calculations? It's analysis of that building thermal envelope where you analyze every square foot of exposed thermal envelope and identify how much heat's going to be flowing through it. It's that simple. We just look at every square foot, the whole thing, and we look at how much goes through it by conduction and how much is going to leak through it. And then we look at how much heat we produce inside the house in the summertime, so we can account for that. Any ventilation air we bring, and we come up with a number for our heating and cooling. And if we do it right, we have a system that's more efficient and more comfortable. The goal is big enough to be comfortable, but no bigger. I bet I was asked 500 times by someone calling me and saying, hey, so-and-so referred me to you. We need a new furnace and we want to add air conditioning, but we need a big one because the room at the far end of the house is cold all the time. Does a big system fix that? A big system makes it worse because it turns on for a short cycle and shuts off. Turns on for a short cycle and shuts off. Now, most of us now, we drive a vehicle that we can set a temperature, not all of them, but most cars now, if you buy a new car today, you can set a temperature and the fan speeds up and slows down and the heat changes to what? To where we are adding heat at the rate that we lose heat. So back in my older vehicles, when it's cold outside, you start it up, you warm it up, you're headed on a long distance trip. What do you do with that has just a fan control and a temperature control? You fiddle with it, don't you, until you don't have to touch it. Isn't that our goal? Have you ever ran your car heating system by, you heat it up, when it gets warm, you shut it off, and then when you get cold, you turn it back on? Why? Would that be comfortable? It would not be comfortable, would it? Well, that's how we heat our houses, isn't it? We heat it up to a temperature, then we shut it off. Heat up to a temperature, then we shut it off. If we are closely sized, it's going to run a longer cycle and it's going to be more comfortable and it's actually more efficient. I drove to St. George and back twice in the past 10 days, 12 days. And I could go there two ways. I could set my cruise control and go at a fairly constant speed all the way, and I could get there in 4 hours and 15 minutes. I could, if I wanted to, started and stopped and go at 100 miles an hour while I was going, and then stop and go at 100 miles an hour and then stop. Which way would use the most gas? By double. The starting and stopping. It's the same thing on heating and cooling systems. We start and stop. We heat up the heat exchanger, or we start the air conditioner. We move the refrigerant. We get it to where it's working right, and then we shut it off, and then we start all over. Every time we start a motor, we draw a lot of current when the motor starts. There's no reason to put grossly oversized equipment, and every reason to put more closely sized equipment. And I'm not going to spend a lot of time on this. Simply, I'm just going to touch on some of the key points. The code tells us that you must do a load calculation in accordance with Manual J or other approved methodology. Select equipment through ACCA Manual S. And then it also goes on to say that we do our ducts in accordance with ACCA Manual D. And the efficiency rating needs to meet the federal standards for the geographic location. I could do a 3-day class on this subject right here, and we just barely brushed the surface. And so we're not going to do that, but we're just going to talk about. We need to have a load calculation submitted and done correctly. And then we need to verify that the equipment they install matches the load calculation. And why did I put the $1 Harbor Freight screwdriver on there? Because you might need it to open the furnace to see what the model number is. So verify against the load calculation what equipment's installed and the condenser at final. And I'm just going to leave it at that. If you want to see more, we have some videos on the website, the UtahEnergyCode.com on Manual J and D and S. Let's talk about something else that we miss all the time. This is on our sheet. What is mechanical system piping? What would we consider mechanical system piping in a residential code? I'm sorry. That's mechanical system piping. Yep. And the suction line, the bigger line, is cooler than 55 degrees. And so we have to insulate it. What other mechanical system piping might we have? Not our potable water. That's separate. What about our boilers? We see any boilers in residential homes? Doing snow melt systems, doing radiant heat, all that piping we call mechanical piping. So our mechanical piping is where we're using a fluid for a heat transfer. So it might be a glycol solution, it might be a water solution, you know what I mean? Where we're transferring heat through that. And we actually have some kind of hybrid systems where, and I think some of you have seen these apartment projects. And these kind of make me nauseous when I think about it because of all the problems I've seen with them, that they use a water heater. They put a water heater in the apartment, and that water heater serves both the potable water, your hot water for your bathing and cooking and showering, and it's also your heat source for space heating. So they do. You haven't seen one of those? They're everywhere. They put a little bit bigger water heater in there. They just take a pump, grab some hot water, run it off into one of those little flat pancake air handlers. You've seen them, haven't you? You probably reviewed apartment projects that have them in it because it's very popular. Think how cheap it is. You buy one water heater, just a little bit bigger, one of those cheap little flat air handlers, and a pump and a few things. And you use the hot water from the water heater to heat your space. And when it's really, really cold, you're probably not going to have as good a shower as you're going to have when in the summertime, because you don't have enough hot water, right? Not everybody is aware of some of the problems you have with that. What's the first problem you're going to have? Let's think about this for a minute. So we're pumping water off of our water heater out through some pipes to a coil, and then we're bringing it back.
Losing the heat.
Now, it's just a little bit of water. You still can shower, but if it's cold outside and it's running a lot, you're not going to have enough hot water. What happens in the summertime? So when the thermostat calls for heat, it just turns the pump on, and it turns the fan on in the air handler. That's all it has to do. So we turn on the pump, we put hot water running through this coil, that we blow air over it, we blow heat into our space. Simple. We don't have to buy a furnace. We buy one air conditioner for outside, we buy an air handler, a pump, and we grab the hot water off the water tank. So in this,
Talking about Legionella.
I'm talking about Legionella. What's Legionella? It's bacteria that grows in stagnant water.
In warm water.
Warm stagnant water. So we have air, we have water sitting in this coil all summer long, but the pump's not running. And so it sits there for 4 or 5 or 6 months in that piping and that coil until it gets cold and someone turns the thermostat back to heat.
And the water gets restricted.
The pump turns on and it brings all that water that's just been sitting and mixes it back in with your, and Legionella spreads through your respiratory system. When do we ever inhale moisture? Every time we shower, right? Now, some companies have recognized this, and I'm involved in litigation on one of these cases right now. But some companies have recognized it, and they build in their air handlers for this very specific application that every day or every 8 hours or something, the pump turns on.
Got a recirc line or something?
I'm sorry?
It's got a recirc line or something? So
Well, it already has a recirc on it,
it just moves that water.
but it just turns on and it runs the pump for a short period of time. So it just exchanges the water. And yeah, it puts some hot water, and then the air conditioner has to remove just a little bit of heat, but at least it refreshes the water a couple times a day, so we don't grow stuff in it. It's not energy code, but it's part of the code, and it's part of, that's mechanical piping that runs there. And it's really affordable way to put in a system. Guess what the other problems are with it? Anybody ever seen a frozen air conditioner where the coil freezes over? And it just keeps growing ice until you shut it off? Well, these little air handlers have air conditioning coil and hot water coil all built in the same little slab. So they have 4 rows of air conditioning coil and 2 rows of hot water coil. And you freeze the air conditioning coil, and the ice grows and encapsulates that hot water coil with stagnant water in it and freezes the coil. And what happens? The coil bursts, and what's it hooked to? Full house pressure. And you got water everywhere. And you put in a 6-story building, the one I'm thinking about in particular, and it just pours gallons of water, hundreds of gallons of water if someone's not there to shut it off. So these are a little bit, they're indirectly part of the energy code, but there are things that I think I need to bring up because I bet you see lots of them, don't you, Alexa? Because it's very, very popular. If you ever have a question on one of those, send me an email and I can share some more information, because it's a system that works, but you just got to do it right. They have to be maintained.
The ones throughout like the senior care centers, that's where I see a couple of the Legionella.
Yeah, yeah. Yep, yeah, you have to,
Those are just fatal.
Yeah. yep.
Those patients are already
If a patient in a care center gets Legionella, they're gone, just kind of like COVID with them. You know, it's what got me off on that track was the mechanical system piping. So that piping from the water heater to the air handler and then the return line back is mechanical piping because we're using that piping to transfer heat from one place to another. So it needs to be insulated for R3. The other thing that gets missed all the time are recirc pumps. And I'm sure many of you have seen these on homes. You have a big home, you don't want to wait forever and waste all that hot water, cold water that you throw away while you're trying to get hot water to the shower or to the sink. So they'll put a recirc line in. So you take hot water out all the way to the end, and then you put a return line and you run a little pump. So you maintain hot water in a loop all through the house, and then you just have short branches. If you have recirc, you have to insulate it to R3. So that whole loop needs to be insulated. And I bet we don't catch 5% of those because I've missed it before. I go there on rough inspection and I don't realize there's a recirc loop. Everything's fine. You get to final, we see a pump and all that recirc stuff installed and it's all drywalled and we didn't get that loop insulated.
Is the insulation up there in the left-hand corner? Is that what you would insulate it with?
Well, there's that and there's the black stuff that, but it needs to be R3.
Is most of that insulation made for that R3?
You can get, it depends on the thickness, the rubberized stuff,
Right.
you might have to,
Minimum, do they have a minimum R value on this and that?
some of them are less than R3. You got to make sure, you have to make sure the product is R3.
What are, so sorry, I was just reading that, some exceptions, so hot water piping's on that slide, but the bottom one, 403.5.3, some exceptions, what are the exceptions?
There's a system, and I'm trying to remember what they call it. I think it's the demand hot water system that actually uses the return, the cold water line for the return. And it senses. I'm trying to remember how those work. Maybe their time of day or anyway, it's not a return loop. They actually, some of them, I think, I'm trying to remember, one of them has an occupancy sensor on it. So when someone walks in close to the,
Next slide has. They come down. Got it.
that's not what I was looking for. Yeah, demand recirculation. So it actually returns through the cold water line. And so it senses there's going to be some, that there's occupancy in the bathroom, and it'll actually turn on a little pump underneath the sink. So it'll pull some hot water up on the hot water line and return it on the cold water line. We're not doing this continuous. And so it's just,
That's the IRC, that code section?
all of these are,
R.
oh, actually, these are out of the IECC. And I probably should have mentioned this right at first. I wrote this based on the IECC. Chapter 11 in the IRC is exactly the same as this code. But what you'll be is 1104. So it'll be 1104.5.3. So it's chapter 11. Yeah, and thanks for bringing that up. So here's an example of one, and this one's actually installed incorrectly. We have a water heater, and we notice the pump. And which side is it on? Is it on the cold or the hot? Can anybody tell from that picture?
Looks like it's on the hot.
It's on the hot. Because here's the shutoff, right, on the cold side. So bringing the cold in and into the water heater, up to the expansion tank. the pump isn't supposed to go in the main hot line. It's supposed to be on the extra small return line that you bring back to the water heater. The way this is installed, all the hot water that's used in the house runs through the pump. And there's actually going to be friction losses because the pump isn't always running, right? So this one's installed incorrectly. But that being the case, if it was installed correctly or incorrectly, this whole loop should be insulated. This is the return line right here. So this pump should be mounted in that return line. So it pulls hot water up and around and then dumps it back into the cold side so that we maintain.
So it takes another line.
It takes an extra line coming back from the far end. So you go all the way out and you might start 3/4 or 1 inch and go out, take all your branches off. And then the farthest fixture, you can take a 3/8 line or a small line and bring it back, because all we're going to do with a pump and a timer is during occupied hours, we're just going to run the pipe and keep it warm loop. But we're basically a radiant heater. It's radiating heat off the line the whole time. And so in the summertime, you have to remove it with air conditioning. But it needs to be insulated. So here's where our domestic hot water needs to be insulated. And again, there's some exceptions, and you can't put them all in a small handout, but if it's greater than or equal to 3/4 inch pipe, we never do that, but we should. If it serves more than one dwelling, located outside conditioned space, from water heater to a manifold. I have a manifold in my house. It should be insulated to the manifold. Located under floor slab, that's been amended out by the legislature. Buried piping, now I don't know what the difference is here, because they're both, well, this is any buried piping. It could be outside the building. And supply and return recirculation systems that we just talked about, with the exception. This was amended out again for Washington County because they build slab on grade. Where do they run all their water lines? They run a whole bunch from underground, and they don't want to have to insulate them all. But how quick does the ground take the heat out of a pipe? Incredibly fast compared to how we give up heat to the air. We take it away a lot quicker with the ground. Some other just a heads up, we are going to go, I guess we'll take a break around 3. Does that sound right?
Yeah.
And then we will leave when we finish. They say 5 o'clock. I don't think we're going to be here till 5 o'clock. It's about 4 o'clock. I know what all your eyes are going to be doing. You know, it's that deer in the headlights look. I've seen it many times, and I get it too. Couple other things in the energy code. When I first started teaching, well, we've already talked about equipment sizing, so I don't need to go over that anymore. Snow melt controls. When I first started teaching those Morningside energy code trainings up at the state capitol, and people were ranting and raving about why are we enforcing an energy code, because we have people up in Park City and everywhere that are melting snow. We're making them build an efficient house, and then they're putting in a 1 million BTU boiler to melt snow. I guess it's a valid point, isn't it? Because we're wasting up melting snow, should we say, well, we'll waste it on our house too? I don't know if that's very good logic, is it? And I don't know if it's really that simple that melting snow is always wasteful. How much money do some areas spend shoveling snow and trucking it out of the area because they have no place to store it? Happens all the time. Park City even looked at putting snow melt in Main Street. because of how much it costs for them to, they literally go in with payloaders and scoop up the snow, dump it in dump trucks and take it out and dump it someplace. And at some point in time, where are we using the most energy? You know what I mean? So the next best thing that we can do right now, and maybe we can come up with something better, is if you're going to melt snow, you have to put a snow melt control system on it. Now, I installed some snow melt systems, and I actually had customers that said, I don't want to spend the $1,200, $1,400 for a snow melt control. I'm just going to, I'll watch the weather, and if it's going to snow that night, I'll turn it on. And then they forget about it. And so it runs for days. Or others that have so much money that they just idled their system. They just let it run. I don't care if I spend $2,000 a month in gas. My driveway is always dry. You know? Yeah, give it to you, right? Yeah. So what does a snow melt control have to have? It has to sense slab temperature, air temperature, and moisture. And guess what? They work. They work really, really well. I was doing a system up in Park City, and I was down there and I was just wrapping up the loose ends. I just bled all the air out and everything was going. And all of a sudden the boiler clicked on. And I hadn't done anything to it. I go, what the heck's the deal? Walked outside, it had started snowing. And we just had this little skip of snow that it would start to collect on the driveway, and the snow melt had turned on and you could see where the tubes were. And I mean, it was working. The conditions, you know, it had been cold already, but soon as the moisture hit it, we had all the three ideal conditions. It was cold air, cold slab, and moisture. And then it turned on. And as soon as we're dry, it doesn't matter if we're zero, it shuts off. So that they actually work well, and they maximize the efficiency of the system. So,
for somebody that I have not the other days, but I can put Park City on it. Is that like a radiant heating? Basically that.
Yep.
That thermostat.
Yeah, it's, you put welded wire mesh. This is the way we did it. You put welded wire mesh down for the whole driveway, and then you run the tubing, and you have to do a calculation. But you run tubing generally on 1 foot centers back and forth, and you'll have a lot of tubing in a big driveway. And you'll have zones, you know, you only so much tubing because of friction and stuff. It hooks to the control in a boiler. You have a glycol solution in it. And its whole purpose is to heat up the driveway when it's a radiant heat. It's just like we do radiant heat inside a house. But you have, of course, you have to put an antifreeze solution in it because it would freeze. Go on YouTube and look at snow melt systems. They got some pretty good videos there that'll show you.
I see them all the time, but I don't know if I've ever seen a snow control system of snow melt control.
Yeah, for all you inspectors,
Always look for it when you're doing the pressure test.
Yeah.
when you're doing the pressure test, you should be looking for a little brass cup. And they should have a little piece of 1/2-inch conduit, plastic conduit or something running from it, so that they,
To the boiler. So
yeah. And the wire comes, like 50 feet of wire comes on this. This is the cup and the sensor. So you don't put the sensor in when you pour it, you come in and set the sensor after. And, but yeah, that you can,
That's pretty distinguished, yeah.
yeah, and you, so if you go on a pressure test on a snow melt system, ask them where their sensor's going.
Usually it's closer to the boiler than farther away.
They should be located in a spot that's
Gonna be the cold.
representative.
Yeah, it's tied to this, to the boiler itself. So once that cell gets actuated, then it turns on. the
It's like the
boiler.
thermostat,
Yeah.
but it requires moisture too.
You have one for all of its own. Yes. One for.
Yeah, I mean, I guess if it was a huge area, you'd want to go into manufacturer's instructions, and the Tecmar is the one that makes the most of these, and they were probably going to tell you only use one sensor for so many, like 10,000 square feet or something like that.
electric systems, but sometimes I'll see.
Oh,
that.
yeah. Yeah, they have electric snow melt systems, but they still have to have the same thing.
So
Yep.
that's your backyard and all your grandkids there, huh?
I'm sorry?
That's your backyard and all your grandkids in the pool.
Actually, it's my neighbor's pool. You know, we have to be careful nowadays because everybody has ownership of all these pictures, right, Alexa? And so I try to, everywhere I go, I take pictures now so that I have pictures that no one can say, oh, that's a copyright infringement. So, so yeah, I took that picture. And it's our youth group. The boys out there going swimming. But why is it in there? Because pools and in-ground spas have to have readily accessible switches for heaters and timers and pumps and heaters and vapor retarder covers for all pools, if the pool is heated. And again, we have exceptions, and one of the exceptions is if you're using waste heat, like if you have a heat pump and you're using the heat you sucked out of your house with air conditioning, you can use that. Or if you're using solar panels or something like that, you know, thermal solar panels, those are exceptions to it.
Some of the operators that put the cover, we've done a few rec centers and it's like, yeah, we have to provide the covers, but you know, they hire like 16-year-old kids to run.
To clean it.
Yeah, and like, and operate the pool system. And they never put the covers.
Yeah. Yeah.
Not neat.
Actually, the code, they put in the code a few code cycles ago that they had to be insulated covers. And it was impossible to meet because you can't roll up the cover. And so now that's just a vapor retarder cover to try to keep a little bit of the heat inside the pool. Because pools use a lot of energy too. They really do. But you know what? People are going to do them, and the code isn't going to go so far as to say, well, you can't put anything in your house that uses energy. I mean, the power company, you know how the Rocky Mountain Power sends you these things and they'll tell you you use more or less than your neighbors, right?
That's just as annoying to me.
Well, and I've done all these improvements on my house and then they keep telling me you're using more. No kidding. I have a 5-horsepower air compressor out my garage for my shop. I weld. I do some stuff that uses energy. And I pay for the energy because I want to do those things, right? My air compressor draws a lot more than my air conditioner.
Same as you all convert electrical stuff in.
Say that again. I know it, those, they drive us crazy, don't they?
Supposed to convert to use electricity for heating, cooling, and everything.
Yeah, we're supposed to use electricity for heating, cooling, and everything now. My brother lives in San Jose and they're saying the no natural gas. And the question Steve asks me all the time, so where are we supposed to get all this electricity that we're going to have now? So that's a whole another question.
Well, they still send it to you even after you have solar panels. It's like, come on, you know.
Yeah, I don't have solar panels, but
I do, and they still send it to you.
and you know what? I also, my sweet wife of 48 years, her feet are always cold. Do you know what she uses? Those little space heaters to blow on her feet. They use 3 times as much energy as any other heat source. But guess what? I pay the bill.
Because it's just as much right here.
Yep. At least the house isn't quite so hot. But you know, we do the best we can. We build an efficient house and then we use some energy for the things we like to do, right? I'm not going to give up my big air compressor. Anybody ever had a 2-stage air compressor? Would you ever give it up?
Nope.
You never have to wait for air.
Mm.
All you guys with single stage, you know, you loosen all the lug nuts and you have to wait for the compressor to catch back up. Doesn't happen, does it?
Nope.
At rough and or final, verify we have programmable thermostat. Heat pumps. Some of you are aware of heat pumps and how they work. A heat pump is simply an air conditioner that reverse cycles. So what it does in the winter time, it pulls heat out of the outside air and brings it inside. Now, the colder it gets outside, the less heat we have outside, but the more heat we need. And so at some point in time, with an air-to-air heat pump, we might not have enough heating capacity with the heat pump, and we might have to put a strip heater in there, auxiliary heating. Now, that auxiliary heating uses a lot of electricity.
With the new air pumps, because your refrigerant is like at a minus 50 degrees, it can get, really cold air.
Yeah.
It can still capture heat.
Yeah,
You're affected.
yeah. The Mitsubishi makes in their variable refrigerant flow and their multi-splits, they have what they call hyperheat or something like that. And because they're using different refrigerants, they can do better. Jennifer.
So do you have much work with like larger homes and stuff like that? I know some of them are pushing like ground source heat systems.
Ground source heat pumps they work, but they're so dang expensive to
Well,
install.
And the funny thing is that after, well, I won't say where I was at before I went to the state, but anyway, we did that in a couple of schools, and that was supposed to be such a great cost saving thing. Well, yeah, the boiler didn't have to heat the water as much, but the electricity was ridiculous. It
Yeah.
was, and the way they set it up and everything, it was a mess. The first couple of schools.
For schools and things like that, it makes sense.
I've seen them a
For
lot in
mass
schools.
restrictions, but not for a residential home unless there is a freaking
Yeah.
mansion somewhere.
Yeah. Now, these are great questions, and so I'll just touch on it. So let me finish up with the air-to-air heat pump, and then we'll go to the ground source. So the air-to-air heat pump takes heat from the outside air, and like you say, they're getting better now.
Yeah, the 300 degree minus is, there's heat in the air.
Yeah.
From below.
You have really low evaporation temperatures. And because of really low evaporation temperature, outdoors, you can absorb heat out of 10-degree air. Yeah. But let's start with that premise. We're taking heat from a colder spot, and moving it into our warmer spot. When we do ground source heat pump, going in the opposite in the summertime, we take heat from our inside space where we're in the 70s, and we're dumping it outside where it's 100. So we're moving it from a cooler spot to a hotter spot. And we do it through refrigeration. We play with the pressure and the evaporation and everything, and we could do a whole class on that too, couldn't we? Ground source heat pump, the theory is fantastic. The ground, when you get down in the ground, is 50, 55 degrees. Great place to pull heat in the wintertime because we have a fairly warm outdoor condition. You have to make sure you have enough wells or loops in the ground and everything, and we can pull heat. But they're fantastic in the summertime because we're dumping heat, moving it from 70-something degree inside and dumping it in a 50-degree outdoor condition. So they have SEER ratings in the 30s and 40s. However, we did a project at Salt Lake County. It was a community center up on Evergreen. Tore down an old library, an old fire station, built a new community center, and it had a senior thing, and it had a library. It just had all these, a gym and all this stuff. And they did it all with ground source heat pumps. And they had 72 300-foot deep loops in the ground. So 72 holes drilled 300 feet deep, and then you fed a pipe loop down into it, and you buy the loops manufactured with the 90 on the bottom, and you drop 72 of those 300 feet in the ground. And then there's your ground source. So you dump heat or you pull heat out of it. Now, there is some advantages in schools and in centers like that that have a heating load and a cooling load, because they bring that water that they bring from the ground, and they run a loop all the way through the building. And then they hook the heat pumps to that water loop. And there's times that part of the building is cooling, so they add heat to the water, but that water is making its loop around. The other part of the building that needs heat can grab the heat out of it. So in schools, we'll do that too, or big buildings that you always need to cool the middle and you're heating the outside. So you can heat and cool and just move the heat around in the building. And if you need to dump some in the ground, you dump it in the ground, or if you need to pull some out of the ground, you bring it back. Guess what? We have some really great technology that doesn't require 300-foot loops, 72 feet in the ground. Variable refrigerant flow heat pumps. They're very, very efficient. They're 25 SEER and stuff like that. We have very efficient gas furnaces, very efficient boilers. We have solar systems and all this other stuff. So I've watched it over the decades. This is the solution. You know, there were some solar systems back in the 70s. They were the solution. Then it was ground source heat pumps. Then it's, you know, I mean, it's the new sexy term, whatever it is, and that one's going to solve it all. Then it was bubble foil insulation that you put in your attic, and it's going to reflect all the heat, and we're not going to have any air conditioning load anymore. And then it's, oh, you put in, and it's come around again, you put in this whole house exhaust fan that you turn on at night to clean to sweep all the warm air out of your house, and you don't have to run your air conditioner. And guess what? Each one of these things might make a difference, and it might be better in one than another, but it's not the solution. The solution is build the very best envelope you can, ventilate it properly, and then you don't need a lot of heat, and you don't need a lot of cooling. You know, you have solar panels on your house. If you had a brand new house, I would tell you, Jennifer, if you have a brand new house and you got 30 grand you want to spend, I'd say build your envelope $30,000 better. And then in a few years, put your solar on. The existing house, great, put your solar on. You reduce it some, but you could have also improved your envelope. They both are viable options, right? You agree with that?
Absolutely. Yeah, it's all about envelope to reduce the peak loads, right? And so you don't have those crazy demands. Let's just use that, but you don't have crazy demands.
Yeah, so Facebook just built, well, they're on, what number of buildings are they on? Do you know?
Like 5 or 6.
I was involved in the first big one they built out there in Eagle Mountain. Almost 1 million square feet, 950,000 square foot of data center. Can you imagine the air conditioning expense on that? Do you think they did ground source heat pump? Guess what they did? Evap cooling. The whole thing. There are, they're shaped like an H. Each long leg is 1,200 feet long. And they have great big fan walls that bring in air from outside, filters that run for 1,200 feet, or it's broken into sections. Evap cooler pad, you know, the big manufactured pad that stands 14 feet high. And then they exhaust a certain amount out, they recirc some. They're not doing any refrigeration for that huge data center. Think how much they're saving. There's no ground source heat pump, there's no VRF, there's nothing that is more efficient available today. What? It's okay, but the envelope isn't that big of a deal because they're moving all this air through it. And they produce so much heat in the wintertime. Yeah, and they have it ducted down into cold aisles and, you know, hot aisles. And have you seen it?
I haven't. Is there a moisture issue with that?
Well, it's pretty easy to control.
Is that a big thing?
Yeah,
How you
we're
control
in
it?
Utah.
Huh?
We're in Utah.
Yeah.
So they just got a dehumidifier system, right?
They don't need a dehumidifier. You just do less evap and mix in some dry outside air. Our air is so dry, we
Yeah,
just
that
don't.
one's here, exactly. I read about it, that you cannot do it in any climate zone.
No,
Right.
it wouldn't work.
Like, it's not exactly as you are talking.
That's why
about,
they're
it's
here.
not like a solution for everything.
No,
right? So
but it's here, it works
that's
here.
In the humid areas, you have another state that works.
And how much water?
And that's been here for a long time, frankly. We have that on our campus.
Yeah.
So, BYU.
Yeah.
BYU, we've been doing.
You've been doing that.
For 30 years, I think 20 years.
Yeah.
We've improved the technology over time. But
Air exchange.
we actually built a new plant on the north end of campus, 5 years ago. Works great.
So
Yeah.
how much water do they use?
Oh, they use some water, and that was my first
Us-
question.
Us being in the second dry state.
Yeah, ours is a closed system within the cooling side, but you're right, on the cooling of the cooling towers, remember? You're using up some water.
Yeah.
It's not enormous.
They have water treatment and stuff, so they collect, they don't, typical about coolers, you dump some water, right?
Yeah, we're not.
They don't, you're not dumping it and they're not dumping it. All of our high-end commercial buildings that are being built nowadays use evap cooling. They all do.
Well, I personally would rather have that than an air conditioner. in my
Well-
house.
Well, I'm kind of,
This is more commercial.
Well, I mean, just when we switched over,
Yeah.
I would rather have
yeah.
the feel of it is better.
So a commercial building now, and we're a little off subject, but that's okay. It's, I think, of interest. A commercial building now will have outside air economizer. And then they'll have what we call indirect evap cooling. And that's where they just take cooling tower water that you've cooled through the cooling tower and run it through a slab coil, adds no humidity to the air. And then you have direct evap cooling, which is a big slab of that cell deck cooler pad. And then if you need it, you got your chiller coil. And so we have 3 stages of cooling literally before we have to turn on the chiller: economizer, indirect, and direct. And my son, he works in, in commercial buildings and across the Western United States. And those systems in Utah and Arizona and Nevada, generally, if they maintain them properly, this ties back in the commissioning, making sure the building's set up properly. Chillers aren't even turning on until in July when we start getting humid thunderstorms. You experience the same thing?
Also,
It's-
when you get the August time.
Yep, late July and August when we get a little more humidity. And the building management systems, the control systems, I mean, they take care of getting too humid and everything. They can maintain it at just a really tight humidity range, just like, the Facebook building, they have pressure sensors and humidity sensors everywhere, and all these dampers and mixing and everything. The first building that came through, George gave it to me and I started reviewing it. What in the hell are they doing here? Because it was, the whole top of the building is air handler penthouse. Just massive. It's really fascinating, but it ties back in. Heat pumps are one part of it. Evap might be part of it. Variable refrigerant flow might be part of it. We have all these things, and no one thing is perfect for everywhere or every application. We have to consider everything and then make our decisions based on that. If we're using a standard air-to-air heat pump, and this is where we got started on this conversation, we don't want those strips turning on unless we absolutely have to have them. And so the code does require us, if you have that electric supplemental heat, that you have a thermostat outside that senses outside temperature, and it won't let the strips come on if we have enough heat outside to meet our heating need. So, if you go to a standard residential heat pump and crank up the thermostat, it'll kick in the strips unless you have a thermostat outside to hold out the heat strips. Because the heat pump can do it, it's just going to take a little bit more time. Boy, we took a beer off there, didn't we? Oh, well.
Geothermal would do it every time.
I was gonna say, the only tricky thing about that, building redesign is if you're doing a hybrid, you just have to make sure that you isolate those locations, so you're not, anyway, like I said, people are messing around with that.
Yeah,
And you just have to make sure you're not mixing those two air
yeah,
condition types.
yeah, yeah. Yeah, we don't want to.
So we should-
Yeah, I just had a conversation the other day. I'm doing an addition on my home. My existing house is evap cooled with just the basic evap cooler. And we're gonna put mini split in the new. Is that okay? No, it's not okay. Because what do? You're adding a bunch of humidity that you're really not controlling. And then your refrigerator system is gonna be trying to pull it all out. So that doesn't work. These big systems are usually about cooling. They have the controls that maintain the humidity in a proper range. Very good, thank you. Yeah, and here it is. Roughed in that snow melt thing before the driveway's poured. Timer switches and 75% high efficacy lighting. This used to be a big thing that we argued about and the state amended it and everything else. High efficacy lighting is a no-brainer anymore. Does anybody here still buy incandescent light bulbs or CFL light bulbs?
Can hardly find them.
Oh, just because of the way they look, it's in our mind.
Yeah, and that's fine. I'm kind of going crazy. I go through Amazon and see which one has a cool LED looking filament in it, to put in my porch lamps and stuff like that. But they don't use anything. It used to be when you put floodlights on the back of your house, you had to be careful. Let's see, 500 watts and 500 watts. And does it matter now?
They're gonna catch fire.
That's just like all the time I spent putting all the cat five in the basement when we finished it. And,
You don't use it?
well,
Yeah.
depends, but no.
Yeah. It's nice to have, but yeah, the lighting has really, in the last, I did a coffered ceiling in my family room with little lift out panels so that I could get to plumbing and stuff like that. And so it's hardwood trim and then with lift out panels. And when I did it, I think it was like 8-9 years ago, I bought 4 little LED can lights, just little tiny ones. I think I paid $40 a piece for them, which is crazy. And now I can buy one of those little ones that I can just install on a little box, for $5 or something like that. And it's so much more efficient. So anyway, that's not a big deal. That's easy to meet. Had the 21 code just says everything needs to be high efficacy. Now there's still, my wife doesn't do it anymore, but she used to have one of those things that you put scented wax in and you had to have a incandescent light bulb so it'd heat up enough to melt the wax. Remember the easy bake ovens? Those of you that are older, even you remember, you had one? Yeah, they've been around for a long time. My sister's had one. How do you use it today if you can't find a 100-watt incandescent light bulb?
Keep this your hard press gooey inside thing.
Yep.
Yeah, you get sick because you think you're cooking it, it doesn't really cook and then you get some like salmonella or something.
Yeah. It's the same thing with taking the drop light and stick it under your hood when it's cold. The 100-watt light bulb. Why did that work so good? 90% heat, 10% light. That's why incandescent light bulbs work well.
I see the T8s up there. We've begun, 5 years ago, moving away from T8s completely off campus. And what we really like is you can take the drivers. Now, this is much more commercial than ever residential.
But that's okay.
You can put all the drivers in an analyzed location because the drivers and things go first.
Yep.
So you can solve all those problems. Real simple.
Yep.
Well, and you probably don't have a problem. Early on, I know we would spec that and you never got the right ones. And they wouldn't check them until they get these energy bills. It was like something's wrong here and then go back and find out all the tubes, they weren't
The right tube.
Yeah.
It's really what my son tells me is all the new buildings with new lighting and the ones that they've converted with the correct lighting, it's actually eliminated a position in the building. You get a big building and you have someone that's changing light bulbs all the time,
Save FTEs.
you know, because fluorescent tubes, they start flickering and someone's got to go change either the ballast or the tubes, you know, and there's people that's all they did all day, every day in big buildings, because it was a constant thing. It's like painting this Golden Gate Bridge, you know, it's, you never stop. So we've really come a long ways, and I imagine you've noticed a huge difference. And
Oh, absolutely. It's so much easier. I'd never put T8s in again.
yeah,
Never did.
yeah, and I don't think anybody is, you know. I think my slide's 2 years old, so it's outdated. All right. They're doing break right now. Let's take a break.